Example 3.1.9, for the generator in example 3.1.8, determine the output voltage delivered under the following conditions. Rated current at 1 power factor and rated current at 0.8 power factor leading. Also determine the voltage regulation for the 3 different operating conditions analyzed. So in the last example, we determined that the line-to-line voltage, or we were given the line-to-line voltage under a no-load condition is equal to 480 volts. So that's the information that was given to us. We were told that the synchronous reactance was equal to 1 ohm. The rated current is 60 amps. And what we're asked to find here is the V out at I equals 60, power factor equals 1, and V out at I equals 60, power factor equals 0.8. And for both of those, we also need to know what's called the voltage regulation, or the percent change in voltage under load is what that really is telling us there. So in the last example, we found that if we change the load current in a generator once it's been set, that's going to change the output voltage due to the armature reaction. So these are just 2 more calculations about what happens when there's changes in load current due to this armature reaction, or what the effect of the armature reaction is due to these changes in load current. So we found that the generator had been set such that EF is equal to 277 volts. And again, EF is the excitation voltage of this generator. We've got a real simple generator. There's just a synchronous reactance and an EF. And then the output voltage is called the terminal voltage here, or the output voltage on a per phase basis is called the terminal voltage. So we've got EF here is 277. That just came from dividing V80, or sorry, V line to line no load by √3. So that's 480 over √3. So anyway, this is the circuit model that we're trying to analyze. What we want to know is, what is this terminal voltage under 2 different load conditions, Z, so we connect a load and some current flows, 60 amps at a power factor of 1, and 60 amps at a power factor of 0.8. Oh, I guess I should have said this is leading. That's very important. Leading. So big picture, what's going to happen is the magnitude of the terminal voltage is going to change, and the angle of the excitation voltage is going to change. Magnitude of excitation voltage, though, is set by the excitation current, and it's fixed unless somebody adjusts it. So we're analyzing the condition on what happens before somebody adjusts it. So for a power factor of 1, we know that phi is equal to 0 degrees, meaning that the terminal voltage and the current are going to be in phase. So if this is VT, we know that IA is going to be in phase, and that's a 60 amps right there. The voltage drop across this is going to be equal to IA times JXS, and so that means that this voltage here is going to be 90 degrees out of phase with the current, so it's pointing straight up. This is going to be J times 1 ohm times 60 angle 0, which is just equal to 60 at angle 90 degrees. And then finally we've got EF. We know its magnitude is 277. We don't know what its power angle is yet. In fact, we don't actually have to even calculate it for this problem. So anyway, I think you can pretty clearly see how we're going to calculate VT from this equation. VT squared plus 60 squared is going to be equal to 277 squared. Very easy right triangle to solve right here, and that gives us a terminal voltage of 270.4 volts. So that's the terminal voltage if for some reason the load were to change from 60 at 0.8 lagging, if it were to change to 60 at power factor of 1, all of a sudden that terminal voltage is going to drop down to 270.4. We were asked to calculate what the voltage regulation is, and that's just a measurement of how much the voltage changes under different loads. And so the voltage regulation for this is going to be given by the no load voltage minus the full load voltage divided by full load voltage times 100%. And so that's going to be no load. V no load is just EF, so that's 277 minus 270 divided by 270, multiply that times 100. Clearly I'm doing a little bit of rounding here, but that's going to be about 2.6% right there. So we get a terminal voltage in the first case of 270.4, and we get a voltage regulation of 2.6%. Remember though that this terminal voltage is not the voltage that is measurable at the output of the generator. We need to multiply that by root 3. So 270.4 times the square root of 3 is going to give us 468.347 equals the magnitude of the line-to-line voltage at the output. That's actually what would be measurable at the generator's output terminals. So that was the case for a 0.8 power factor, for a 60 amps at a unity power factor. Now let's move on to the case for 60 amps at 0.8 power factor leading, meaning it's driving a capacitive load in this situation. So we've got power factor equals 0.8 leading. That means phi is going to be equal to, let's see, 36.87 degrees positive. So again, we're going to take the terminal voltage VT as the reference, and this time the current is going to lead the voltage, so that's going to be something like this, where that's phi right there, and that's 60 amps. So that's the relationship between voltage and current, IA. What then happens is this IA, I'm going to scroll up, is flowing through this inductor right here, which means it induces a voltage that is 90 degrees out of phase with the current. 90 degrees out of phase with this current is pointing back that direction. So that JXSIA is going to end up pointing that direction right there. So in fact, it's going to be equal to, let's see, that's 60 at an angle of 36.87 times J1, and that's going to give me a value. This angle right here is going to be 60 at an angle of 126.87. Right, it's 36.87 plus 90 degrees. So that's a pretty big vector. EF is going to have to complete the Kirchhoff's current or Kirchhoff's voltage law for that generator. So that's VT plus the voltage drop across the synchronous reactance has to equal EF right there. So that's delta. Fill that in. Remember, the magnitude of EF can't change, so it is still this 277 volts. Again, EF is fixed by the field current. And so now I've got this funny triangle that I have to solve for VT. Again, what I want to do is solve right triangles, the same method. The application's a little bit different. So here's the right triangle I want to solve. 277 is the hypotenuse. The height is the projection of this vector here into the onto the y-plane, and the base is going to be VT minus the projection of this vector onto the x-plane. So hopefully you see that right triangle pretty clearly. And I'm going to write the Pythagorean theorem for this right triangle. It's going to be 277 squared. The hypotenuse squared is going to be equal to the base, which is going to be VT minus, now pay attention here, I want to take the projection of this vector in this direction. So I don't want to use 126.87. I want to use its complementary angle right there. So that's going to be 180 minus 126.87. And so that angle is 53.13 degrees. It's getting a little tight in there, but that's 53.13 degrees. So I want to subtract off the projection of this vector in that direction. So that's going to be VT is going to be equal VT minus 60 cosine of 53.13. So that's a little different than the example for a lagging power factor. Then I need to figure out what the projection of this vector is into the y-plane, and that's just going to be 60 times the sine of 53.13 degrees. Yep. And so I solve that and I get VT equals 308.8 volts. And then to convert that to line-to-line quantity, I need to multiply by root 3. And so that's equal to 534.857 volts line to line. So that's an interesting effect, is that for a generator loaded with a capacitive load, the output voltage actually increases. If we look at our no load voltage, it was specified as 480, but if we throw a capacitive load on that, it actually causes the output voltage to go much higher, 534 right there. We can calculate the voltage regulation here. That's going to be, voltage regulation is going to be equal to no load voltage. I can use a line-to-line quantity here or a phase quantity. Since I did phase in the previous example, I'm going to do line to line here. So that's 408 minus 534.857. So V no load minus V full load over V full load, 534.857. And I multiply that by 100%, and I get negative 10.3% since the output voltage is higher. This is called negative voltage regulation, and this is called positive voltage regulation right there. And I guess the last thing I wanted to do in this example was I wanted to determine the voltage regulation from example 3.18. We found that the output voltage was VT at, I guess I'll say at 60 amps power factor equals 0.8 lagging. We found the VT was equal to 236.8. So the voltage regulation under a lagging load was going to be 277, right, the no load voltage, minus 236.8 divided by 236.8 times 100%. That's going to be about 17% voltage regulation. The reason I wanted to do that is this is the most common operating condition for a generator. It's supplying maximum current to a lagging power factor.